Samuel Taylor is our next speaker from Yale University, and he is going to be talking about counting loxodromics for hyperbolic actions.
Okay, thanks to the speakers for inviting me, and thank you all for coming. I'm going to talk about some joint work with Gekhtman and Tiozzo. So we'll start pretty general and then sort of add hypotheses as we need them, but let me tell you what we are interested in. So let's start with a finitely generated group acting on a metric space X. Okay, and all my actions will be actions by isometry, so G you can think of as living inside of the isometry group of X. And the question we are interested in is, what is the dynamical behavior of a typical element of G? Okay, so we'd like to understand the group G by the spaces on which it acts, and in particular, we can understand properties of that action via the dynamics of its elements. Okay? And we want to know, well, how does a typical element of G act? Okay. So I'll spend the first couple of minutes explaining what I mean by this question. Okay? So maybe the best way of doing so, and just to get a flavor for the types of questions I'll be interested in specifically, let's start with an example. So I'll write the example over here, and it's sort of a baby example. Okay, an example of a surface group acting on a tree. Okay, so how do we get such a thing? Let's start with the surface S. Okay, and we'll let G be the surface group, fundamental group of the surface. And we'll draw a simple closed curve on the surface and call that alpha. Okay? And the action I'm going to be interested in to start with is just the action of G on the associated Bass-Serre tree. Okay? So we can construct such a thing by hand. So let's take the universal cover of the surface, call that P, and take the complete preimage of alpha. Right? So I get a collection of disjoint arcs, lots of them. Okay. And the associated Bass-Serre tree is just the dual tree to this collection of arcs. So we've all seen this picture many times. We get an infinite valent tree. Okay. Only draw part of it. We get an action on a tree. Okay, so for instance, this could be like the type of action that I'm interested in. So what do I mean by dynamical behavior? Well, I just have a group acting on a tree. So there's one of two different ways that an element can act, so maybe dynamics. Okay, so if G is in the group G, it could either be elliptic, okay, which of course means that the element G fixes a vertex, so G fixes a vertex, or the element could be loxodromic. Okay. Just as in the talks we saw before, loxodromic means leaves invariant a geodesic in this case. So acts by translation along a geodesic. Okay. And we could denote its translation length in this case by tau of G. This should be the translation length of that element. So why might you care about this action? Well, in particular, this action tells us about how the element of the group, as a curve on the surface, intersects alpha. Okay, so in this particular case, if G is elliptic, right, this is the same thing as saying that G is conjugate into, well, the fundamental group of the surface minus alpha. That's what it means to be in a vertex stabilizer in this case. Or if G is loxodromic, okay, so this is the same thing as saying the translation length of G is positive. And here the translation length measures the intersection number of the conjugacy class with alpha. So what do I mean by this? I mean the conjugacy class of G corresponds to a homotopy class of curves on the surface. I'm taking the minimal intersection number of that homotopy class with the curve alpha. Okay, so this is very simple. We all know this. But in particular, an interpretation of my question in this case is I'm asking, well, how many times does a typical element of my group intersect alpha in this sense? Okay, so these are the types of questions that I'm interested in. So by the end of the talk, we'll have some way of answering this question. Okay, but of course, before I answer the question, I need to tell you, so that's what I meant by, so here's an example of what I mean by dynamical behavior. In this case, when I have an action on a tree, I mean, is my element elliptic, or is it loxodromic? What I want to do is to next tell you what I mean by typical. Okay? Okay, yeah, so maybe what does typical mean? Okay. So I have a finitely generated group, and so there are at least two good notions of what I can mean by typical. The first one is what I'll call the random walk method. It's very common, but it's not what I want to focus on in this talk. But what do I mean by the random walk method? So what I'll do is, so when I say typical, what I'll do is let's fix a subset of G. And when I say, what does it mean to say that the subset P is typical? I'll think of P as a subset of elements with a particular property. So what does it mean for that property to be typical? So the random walk method, so if I have Gn, a random walk on G, so I'll say P is typical. It's just the probability that the nth step, sorry for the squeaking, the nth step of the element is in the set P goes to 1 as n goes to infinity. So if the probability that the random walker time n is in P, if that goes to 1 as n goes to infinity, I'll say that the property is typical with respect to the random walk. Okay, so we'll come back to this later. But, so that's maybe method 1. But I have a finitely generated group. So there's another way of saying what it means to be typical that uses the geometry of the group. Okay, so I have a finitely generated group, so let's fix a finite generating set. So I'll call this the counting method. Okay, so let's fix, so I'll fix a finite generating set, so some subset of G that's finite and generates G. Okay, and so when I do this, I get a Cayley graph. So this produces for me a Cayley graph using that generating set. And this counting method is going to use balls in the Cayley graph. So remember, the ball of radius n, this is always about the identity, just a set of elements in G such that the word length with respect to S is less than n. It's the ball of radius n. So since my generating set is finite, this is of course the Cayley graph is locally finite, and I can count the number of elements in the ball of radius n. Okay? So a natural family of measures to use instead of the measures coming from the random walk, a natural family of measures to use instead is just uniform measure on the ball of radius n. Okay? So let's make a definition using this notion of typical. Okay, and this is the notion we'll be interested in for this talk. So we'll say P inside of G is generic if the proportion of elements in the ball of radius n that lie in P goes to 1 as n goes to infinity. So if the number of elements in the ball of radius n that also live in P divided by total size of the ball goes to 1 as n goes to infinity. Okay.
Are the properties which are like typical in one kind that's not in the other?
Yeah, so I'll give you an example in a second. I'll give you an example that was actually told to me by Sam Kim. It came out of someone asking that question last time we gave the talk. Okay, so but now that we have some, we can be more precise with our question. We can be more precise. So let's just restate the question. Okay, so same setup. We have a group G acting on X. And the question is, are loxodromic elements of G generic? Okay, so of course here we have G acting on X. This action is fixed. Okay, that's the question. All right, so now to answer your question. The answer is in general no. Okay, so let's just briefly see an example that really illustrates the subtlety in answering this question. And we'll also see a difference between the two notions of typical. So let's see that. So, let's go a little bit out of order with my notes. Okay, yeah. So example. And then we'll have to put extra hypotheses. So we'll give it a situation where the answer is yes. But first, let's see sort of a non-example. So example of answer no. Example where the answer is no. Okay, so let's let G be the free group on 2 generators times the free group on 3 generators. Okay. And let's give G the, so I'll just say with standard generating set. And what do I mean by this is choose a generating set that's induced by a basis on F2 and a basis on F3. Okay. And we'll do just sort of the obvious thing. We'll let X be the Cayley graph on F2. Right, and what's the action? The action is we'll have to tell you how each of the factors acts. F2 acts by the usual action on its Cayley graph, and F3 acts trivially. Okay, so this is just, so G action on X.
Standard generating set?
Yeah, so a standard generating set that's induced by a basis for each one of the factors.
Basis times identity or basis times basis?
Basis times basis. No, it's an actual generating set for the whole group. Yeah. I mean, anything, it doesn't matter what the generating set is. I'm just going to write down an actual number in the end. Okay, yeah, so where F2 acts on X, so F3 acts on X is trivial, and this is the usual action. So, but I mean, let's just note these facts, right? I mean, this is, at this point, everyone knows what's coming, but so first of all, with respect to a random walk, let's say a simple random walk, if Gn is a simple random walk using the generating set, then the probability that Gn is loxodromic, well, this does go to 1 as n goes to infinity. Right, the random walk on G projects to a random walk on F2, and the random walk on F2 is transient. Right, so let's just maybe, in the interest of being explicit, let's say what the loxodromic elements are. Right, so the set of loxodromics, so I'll denote that by lox. So these are the elements AB inside of G, inside of F2 cross F3, where A is not the identity. Those are all the elements that act loxodromically. Okay. And of course, since the random walk, any random walk on F2 is transient, any random walk is the support generates a free group, for instance, is transient, we see that the probability that an element, the probability that Gn is loxodromic goes to 1 as n goes to infinity. Okay. But the set of loxodromics is not generic. Okay. And in particular, you could just write down, I mean, everything here you could write down explicitly, and you would see that if you count the number of loxodromics in the ball of radius n, divided by the total number of elements in the ball of radius n, this converges to 2/3, which is not 1. Okay? Simple example. All right, but I like to tell you about a case where, so what's going wrong in this example? So in our setup, the setup where we have a positive result, we're going to have to, so x here is nice, it's a tree, it's about as nice as possible. It's the group that's the problem. Okay, so I'm going to tell you about the case where the group is hyperbolic. Just like in sort of our motivating example, here S was a surface G, a surface group, which is hyperbolic. So that's the case I'll focus on today. Right, so this example shows us that, well, indeed, the two methods of counting can be different, and it also gives us a case where loxodromics are not generic. Okay, so this is the results of the hyperbolic setting. So let's just go through some setup. So X will be a hyperbolic, say, geodesic hyperbolic metric space. Okay. And just as we saw in Richard's talk, so if I have an element of the isometry group of X, I could define its translation length. Right? So I'll denote tau sub G, the translation length, the stable translation length of G acting on X. So same definition as in Richard's talk, it's the limit n goes to infinity. I'll take the distance between X and its translation by an nth power of G divided by n. And just as what Richard said, it doesn't depend on the base point I choose. So here, X is some element of X. Okay. And we'll define G as in the set of loxodromics. So lox, and it's the set of loxodromics with G acting on X. If the translation length is greater than 0. Okay, so these are the elements I'm interested in, just like in this case. Okay, and as I said, we have to put more assumptions. We can't just let X be a hyperbolic metric space, as we saw in this example. We're also going to assume that the group G is hyperbolic. Right. And then, of course, we need to assume something about the action. Right? For instance, the trivial action on any metric space, loxodromics will not be generic. So we want to assume some sort of non-triviality assumption, and that's simply that the action of G on X is non-elementary. Okay? So let me just recall what that means in this setting. Just that there exists elements of G which are independent loxodromic elements on X. Right, so each loxodromic element has 2 fixed points on the boundary, and independent means that they don't share either of their 2 fixed points on the boundary. So here's the setup for the main theorem, so I can tell you what the theorem is.
So did you say independent meant they didn't share either endpoint or just didn't share both endpoints?
Say it again, sorry?
Did you say independent meant they didn't share either endpoint on the boundary?
They don't share either endpoint. All right, so we'll see a lot of examples satisfying this setup later. But for instance, here's an example satisfying the setup. Okay, but we'll see more later. Okay, so a couple of different theorems I'll state. So here's the first theorem. And so this is with Gekhtman and Tiozzo. So let G be a non-elementary, be a hyperbolic group with a non-elementary action on a hyperbolic space X. Okay, then we get the conclusion that we want. Then the set of loxodromics is generic. Okay, so I'll write it down just one more time what that means. If I look in the ball of radius n, such that G is loxodromic, I divide that by the number of elements, total number of elements in the ball of radius n is goes to 1. Okay. So this is the theorem I'd like to talk about today. So the way I'd like to talk about it is, well, first of all, this is sort of the culmination of a couple of different results. And so I'd like to go through what are those results that lead to this theorem. So where we'll talk about what typical geodesics in G do with respect to the space X. So that's maybe I'll spend the next half of the talk talking about that. And then I like to go over some applications of this theorem. Okay? So in order to prove this theorem, what we first do is study the property of typical geodesics in G. Typical geodesics. Okay, so what do I have? I have the group G acting on X, and let's fix a base point in X. Okay. What fixing the base point gives me is I have the associated orbit map. I'll denote that by phi, which is a map from G to X. Okay, so sending little g to the translation of X by G. Okay, so let's draw a cartoon picture of what this map looks like. So here's G, here's X, here's my orbit map. So there's the identity element, there's X. Okay. What I want to understand is how does it, if I take a geodesic, so let's take a geodesic ray, I'll call it gamma. This is a hyperbolic group, so it has a boundary. I'll denote the corresponding endpoint by eta. What I want to know is if I have a geodesic ray, what does its image look like under the orbit map? Okay, so maybe gamma is a geodesic sequence of elements. So a geodesic in the Cayley graph of my group. A preliminary question is what does the image of this geodesic, which is just, what does this look like in X? So of course I'm not assuming much about the action. The action could be very distorted. So there's lots of different sort of cases one can analyze. So first of all, I have a geodesic in G. I look at its image in the orbit map. Case one is, well, maybe it's kind of squiggly, but maybe it actually converges to a point on the boundary. Right? Case two is, well, maybe it actually has finite diameter. It sort of goes for a while and then stops in some bounded region. Okay? So both of these cases actually occur in this picture over here. Right? If I take a geodesic in the Cayley graph of my group, we could see both of these properties, right? Whether it goes to infinity in the tree or not, it's really whether if I take the path in the Cayley graph of the group, does it cross infinitely many of the green lines or not? Right? If you cross infinitely many of the green lines, you converge to the boundary of the tree. Otherwise, you don't. Otherwise, you're your finite diameter. And there's a third possibility. I mean, it doesn't appear in this case, but a third possibility is the image is completely erratic. Three possibilities. So what we have to first answer is, well, all of these possibilities can occur. What's the typical one? What's the typical thing that happens? So of course, in order to say typical, now I have to tell you what it means. What's a typical geodesic ray? What's the measure you use? And in this case, there's sort of an obvious thing to do. If we're interested in counting in balls, right, that's what we're ultimately interested in, there's a natural limiting measure on the boundary of the group. Right? So if I take uniform measures on balls of radius n, there's a natural limiting measure on the boundary of G, and it's the so-called Patterson-Sullivan measure. So this is a measure on the boundary of G. So informally, it's just what I said. Right? It's the well, it's a weak limit of the uniform measures on balls of radius n. Okay. So maybe I'll try to write down what I mean. So if I let Vn be the uniform measure on ball of radius n, uniform probability measure, what is this? This is, I'll sum over elements in my group. I'll sum over elements in the ball of radius n, the Dirac measures, and I'll divide the whole thing by the number of elements in the ball of radius n. So this is a measure on G union its boundary, okay, which is a compact space. And so a weak limit exists to this sequence. And I'll sort of ignore, well, I should say there's a subsequential limit. And I'll ignore that and just write the Patterson-Sullivan measure. Ignore the subtlety there. Patterson-Sullivan measure, which I'll denote by PS, is the limit, as n goes to infinity, of these measures, uniform measures. Okay. So in general, you only get a measure up to a bounded multiplicative amount because you have different subsequential limits, but they're all within bounded distance of one another. So I'll treat it as if we actually have a limit, just for the purposes of stating the theorem. All right, so what is this? This is a measure on the boundary of G, and we could use it to say what a typical geodesic ray is, right? Okay, so let's over here write down the theorem about what a typical geodesic ray does. So as before, let's fix a base point in X, and we have G acting on X as above. Okay, always is in the hypothesis of the previous theorem. So the statement is that for almost every eta in the boundary of G, so almost every with respect to Patterson-Sullivan measure, and any geodesic ray Gn in G converging to eta, we have the following. So first we have that the typical geodesic ray converges to the boundary of X. So if we look at the image of this ray, Gn times X, in the space X, this sequence converges to a point in the Gromov boundary of X. Okay. So we're typically in this first case that I mentioned, that you converge to a point in the boundary of X. So second, it's that we converge to a point in the boundary of X at a uniform rate. So the limit, so if we look at the distance between X and G and X divided by the word length of Gn, which is just n, right? Gn is a geodesic ray starting at the identity. This equals some constant L that's greater than 0. Right? Where L is independent of eta. So there exists an L just depending on the action, such that typically I go to infinity at the rate L. And third, which is in some sense a consequence of the first two, is that the typical geodesic ray in G, when I project it to X, when I look at its image in X, it tracks a geodesic. So there exists, let's say, a quasi-geodesic ray. R in X, such that the limit of the distance between GIX and the ray, GNX, and divided by n goes to 0. Okay. So typically, a geodesic ray converges to a point at infinity, goes at a linear rate, and stays within a sublinear distance of an actual geodesic ray. Okay. All right, so why is this useful? All right, so our goal is to prove theorem A about this genericity of loxodromics. And what we have is something about what happens at infinity. Okay. So the point is, the next sort of collection of results brings this information about what's happening at infinity, what's happening with respect to Patterson-Sullivan measure, into counting with respect to balls in the Cayley graph. So this. So let's recall that I'm interested when an element is loxodromic. Right, so an element is loxodromic, right? G, let's use my notation. G is in Lox. If and only if its translation length is positive. So I want an estimate for translation length. Right, and there is one just using some hyperbolic geometry. Well, it's well known that the translation length of G is at least, well, so I have my, recall I have my fixed base point. Well, it's at least, well, I take how much G displaces X, and I subtract from it twice the Gromov product between the displacement of X by G and the displacement of X by G inverse. And this is true up to some constant depending on the hyperbolicity constant. Okay. So really what I want to do is, if I want to know that elements are generically loxodromic, I need to really prove two things. Right? I need to say generically I have a big displacement in the space X and a small Gromov product between Gx and G inverse X. Right, so the picture, I think this is a common picture. So here's X. Right, so the displacement of X, Gx, well, it might displace X very, very far away. And that's very good if G inverse X lies all the way over here, because then this is close to the geodesic axis for G. However, it's bad if G inverse, the geodesic from X to G inverse X fellow travels the geodesic from X to Gx for a long time. Right? In that case, I could just be rotating around X, for instance. Okay? All right, so I want this to be big and this to be small. Okay, so let me just state the result that tells us that, in fact, this is big and grows at a linear amount, grows at a linear rate. So, theorem. So G acting on X as above. Then there exists an L prime such that if I look at the proportion of elements in the ball of radius n, such that the distance from x to gx is at least L times the word length of x, word length of g, excuse me, divided by the number of elements radius n. This goes to 1. Okay, so what this is telling me is this is a counting version of the linear displacement statement we had before. So it says generically the displacement of elements in the group grows linearly at a fixed linear rate with respect to word length. Okay? And really this is the first half of the statement we need to show. So really you need to show a corresponding statement that this has a slower growth, sublinear growth. And combining those two statements, you'd get the following. So I'm not going to write down what the corresponding result is for the Gromov product of an element and its inverse, because it's actually more technical to write down. But the upshot of everything, upshot of combining that with the corresponding statement about Gromov products is the following. That G acting on X as above so if I look at the proportion of elements in the ball of radius n such that the translation length of G now, this is the translation length of G on the space X, is at least, okay, so again, so there exists an L prime. Here it's the same L prime. So the proportion of elements in the ball of radius n such that the translation length is at least a fixed multiple of the word length goes to 1 as n goes to infinity. Okay. So since the element G is loxodromic, as soon as the translation length is greater than 0, the element is loxodromic. This tells us, this gives us the main theorem. So the main theorem was that generically elements are loxodromic, but this is telling us that generically not only are the elements loxodromic, but their translation length is growing linearly with word length. Okay, so that's sort of a sequence of results that goes into proving the main theorem. We first prove the result at infinity in the sense of measuring with respect to Patterson-Sullivan measure, geodesics going to the boundary of G, and then use those results to sort of say something about what's happening in the ball of radius n. Yeah?
So would you expect, for example, you could look at the ratio between translation length of G and length of G, I mean, the stable length. And you could ask whether, I mean, this ratio has a unique limit for almost, I mean, statistically, that you know, it should just pick up one number. You think this?
Oh, no, that's what I'm trying to say. So there exists an L, and L is independent of the element.
The L of G over length of G converges to L prime.
Oh.
I mean,
yeah.
Okay. Sort of is near L prime for most elements.
Yeah.
Radius n.
Yeah. So that's true. So yeah. So in this statement, right? In this statement, it's true that you are bounded by. There are more quantitative results that give you what you're saying. For this statement, I don't know about this statement. I don't know about this statement. I expect that to be true. There's just some. It's certainly true for this statement. I have to think about this.
No, because just in the most basic elementary examples of two hybridizations, you get the first intersection. That's what I mean. As the unique somehow.
No. But, so what I like to do for most of the rest of the time is just talk a little bit about applications. Okay, so the first application, sort of the most obvious thing, so I'll just write it down even though it's not, maybe not so much of interest. So of course if I have a hyperbolic group, it acts on its own Cayley graph. Okay. And what do the theorems tell us? Well, first of all, the theorem gives us the statement that, first of all, a generic element of G has infinite order. So, a generic element of G has infinite order. Right, so when I say a generic element of G has infinite order, I mean the set of elements of infinite order in G is generic. That's what that means. And maybe with a little bit more, the statement that has a little bit more content is that the translation length grows linearly with word length. Okay. So that's the first application, although it's what's more interesting is applying the mean result to more exotic actions. Right? So this is the most sort of tame action one can think about. It just tells you that generically infinite order elements are generic. Okay. Well, yeah. We could also think about splittings of our hyperbolic group. Right, so actions on trees. And this just brings us back to our first example. Right, so this example here, well, we had a hyperbolic group acting on a hyperbolic space, and the application tells us that, well, it tells us that generically elements are loxodromic with respect to this action. But remember, being loxodromic with respect to this action told us something about intersection number with alpha. Right, so if we're just interested in this original example, what do we get? So there exists, so going back to our example, where G equals the fundamental group of the surface, there exists an L greater than 0, where L depends on the generating set we choose. Right? So I'm not being explicit with what the generating set is. It doesn't matter except in producing this constant L, such that if I look at the elements of the fundamental group of my surface that intersect alpha at least L times the word length, this is generic. So generically, an element has a homotopy class of curve in the surface, intersects alpha linearly in its word length. Okay. So similarly, instead of actions on trees, you can look at actions on quasi-trees or actions on hyperbolic quotients. So there's various variations on the scheme that one can do. Third is really the main motivation for studying these questions, and that comes from mapping class groups. So motivations from the mapping class group of a surface, closed orientable surface, of genus at least 2. So the question there, asked by various people in this setting, is, well, we have this mapping class group. It's a finitely generated group. And there's a particular class of elements that we're interested in, or the class of elements that Richard spoke about, the pseudo-anosovs. And the question is simply, are pseudo-anosovs typical in the mapping class group? So our pseudo-anosovs, I'll denote it PA, typical in the mapping class group. And just recall sort of the connection that Richard talked about. So there we have the mapping class group. It acts on the curve complex. And the loxodromic elements of this action, well, they're exactly the pseudo-nosovs. Okay. Now, the first thing to note is, well, we have these two notions of typical. One of them was typical with respect to a random walk. And the question is answered in that case. So pseudo-nosovs are typical with respect to random walks. So I'm being, I'm not being very precise with what I mean by a random walk. For any random walk such that the support of the measure generates a non-elementary semigroup, it's true. So for instance, if the measure you start with, its support generates the entire mapping class group, then the probability that the nth step of your walk is pseudo-nosov goes to 1 and goes to infinity. Right, so this is proven by Riven, and this is Mar. Okay. But it's still open whether pseudo-nosovs are generic. It's open whether pseudo-nosovs are generic. It's still open, right? The main theorem that I covered up, right, that doesn't apply. Right? It doesn't apply because the mapping class group is not hyperbolic. So that's sad. So a corollary, though, is, so first, I'll say it's sad because we don't know that the main theorem doesn't tell us whether pseudo-nosovs are generic in the mapping class group, but it does tell us pseudo-nosovs are generic in hyperbolic subgroups of mapping class groups. I'll just write that down, and then I'll tell you why you might care. So let G be a subgroup of the mapping class group. It's the irreducible and hyperbolic. Important feature. Then pseudo-nosovs are generic in G. Okay. Right, so again, you should be sad because this only applies to hyperbolic subgroups of the mapping class group. However, the corollary, because it sort of relies on this fairly general theorem, also applies to out of n. It also applies to right angular n groups. In hyperbolic subgroups of, for instance, out of n, its fully irreducibles are generic. Okay, so the same sort of setup goes through. And even in the case when we're looking at hyperbolic subgroups of mapping class groups, we still have an interesting application. So let me tell you about that. So it's an application to surface groups. Okay, so again, S is closed orientable and genus at least 2. Okay. I want to tell you, what does it mean for an element of the fundamental group to be filling? Okay, so gamma inside of the fundamental group of S fills S. Okay. If, well, I have a gamma, it's an element of the fundamental group. I take, so it's a, in particular, it corresponds to a conjugacy class of curves on the surface. I take the geodesic representative in any hyperbolic metric, and I want it to cut the surface up into disks. So fills S, if I look at S, and I cut along the geodesic representative of gamma in any hyperbolic metric. This is a collection of disks. Okay. Another way of saying that is it essentially intersects every simple closed curve. Okay. Great. So fills. Okay, so then application, corollary. If I look at the elements of the fundamental group of S, such that gamma fills S, this is generic. So So we can even prove it. It's a very simple proof. So there's a map, a homomorphism, P. It's the point-pushing homomorphism from the fundamental group of S into the mapping class group of a surface with a puncture, of S with a puncture. Right, so it takes the puncture and it pushes it around the surface according to the curve you choose in the fundamental group of S. So Richard mentioned this map in the previous talk. And it was proven by Kra that gamma fills S. This happens if and only if the image of gamma under the point-pushing map is pseudo-Anosov. Okay. So since the previous corollary tells us that pseudo-Anosovs are generic, applying that to the fundamental group of the surface tells us that filling curves are generic. Okay. So in the remaining 5-ish minutes, I'd like to give you an idea about how this is proven. Okay, so the main idea is, okay, well, a lot is known in the case of random walks, right? And the idea is to somehow relate the situation of random walks to what's happening in the ball of radius n in our hyperbolic group. Okay, so what we like to do, I'm just going to write this down kind of schematically. What we like to do is to take typical geodesics in G. So this is with respect to Patterson-Sullivan measure, and translate these into the sample paths of a random walk. So translate these into sample paths of a random walk, where the Patterson-Sullivan measure at infinity gets translated to the hitting measure with respect to the hitting measure on the boundary of G. Okay. So let me write down the proposition that makes this rigorous. What does it mean to translate information about typical geodesics in G into information about sample paths of random walks? So we do so with the following proposition. So given G, our hyperbolic group, and the generating set, okay, there exists a sequence of probability measures. I'll note them mu1 up to mu r. So these are probability measures on G. And they have their probability measures with finite first moment, such that you can write the Patterson-Sullivan measure can be written as a sum over elements of G with coefficients AG times the push forward of nu IG by the element G. I want to tell you what these symbols mean. Okay, where so this is the sum, and these are measures on the boundary of G, recall. Okay, where? Well, okay, these AGs, these are just positive real numbers, possibly 0. IG is just gives us one of these coefficients, one of these indices, 1 through r. And nu sub I is the hitting measure, the harmonic measure, on the boundary of G for the ith random walk, for the random walk say, generated by the measure mu I. Okay, that's a lot to write down. The point is that we can write the Patterson-Sullivan measure as a sum of hitting measures for random walks. Okay? The point then is that now we could use this theory of random walks, the theory that I said is sort of, better developed. So then use the theory of random walks for groups acting on hyperbolic spaces. Okay? So in particular, we make use of recent work of Marr and Tiozzo. In the last maybe 30 seconds or a minute, I'll say, so what this tells you is, so suppose you're interested in the first statement, the statement that I erased. It says that a typical geodesic ray converges to the boundary of X. So you take a typical geodesic ray in G, you look at its image in X, and you want to say that it converges to the boundary. Okay? Well, if you knew that for all of the corresponding harmonic measures, then you would know it for Patterson-Sullivan measure. Okay? And indeed, the theory of Marr and Tiozzo does tell you that when you have a non-elementary action of a group on a hyperbolic space, and a random walk, a measure, whose support generates a non-elementary subgroup of your group, then you do get this convergence to the boundary result. What you should be worried about is, why does this tell you anything about the group acting on a space X? I haven't mentioned X. This proposition doesn't depend on X. X is missing from this proposition. The point is what you need to prove, what I won't tell you how to prove. What you need to prove is that these measures you get have something to do with X. In particular, what you need to show is that each one of these measures, well, it generates a semigroup inside of G, and you need to show that that semigroup has a non-elementary action on X. Okay? And when you show that, once you show that's true, then in particular, combining that with this proposition gives you the convergence to the boundary result. Okay, so I think I'll end there. Thank you very much.
Any questions for our speaker?
Probabilistic result follows from your theorem. It's a special case.
So again?
No, probabilistic result.
For the random walk.
In a random
Yeah.
walk setting. It's a special case of your theorem.
Yeah. Well, we use that theory as an input to our
But you
theory.
use it in the proof.
Yeah.
It doesn't give any
No, we don't get anything new about the random walk.
But it's sort of like treating one Patterson-Sullivan measure by using the harmonic measure. I mean,
Yes. So I didn't get to mention it. There are lots of cases where you can't do that. So there's
Right.
many results, right, where, yeah. So what actually happens in this theorem is that these measures, it's been proven, Buzel, Mateus, and Macron, show that this can't happen if these measures are nice. If these measures that you get can't be symmetric and finite support. These measures are non-symmetric and infinite support. And so that's what makes this possible. And you can see how to construct these measures, which are naturally defined with respect to using the automatic structure of G in the defining graph. You look at loops in the defining graph, and from that you're able to construct sort of the support of these measures.
When you say the defining graph, you mean the
I meant the graph, like the
automaton for the
yes.
Yeah.
Yes.
Why did you pick two elements instead of one? Could you show that they're independent loxodromic? If you pick randomly two elements,
Yeah.
you would expect them to be independent loxodromics.
Yeah. So that's new. That's known with respect to the random walk, and yes, that's true. So that's not written down, but it's the same idea, like the idea where you have to show. So what do you have to show? You already know by this the displacement result. What you need to show is that the Gromov products are pairwise, large angle, small Gromov products, and you could do that in much the same way as you show that an individual element is loxodromic.
It seems that there are pieces of what you do that you can do in for the whole mapping class group, but maybe with the Teichmüller metric using the first-order boundary. Do you get genericity in the sense of Teichmüller metric?
So that's already known. That's a result of Joseph Marr. You would have to cook something up. So for instance, you could use, I mean, there are automatic structures in the mapping class group. And you could try to count with respect to a graph directing the paths in that automatic structure. And there you would expect, yes, if you sort of counting with respect to, distance in the flip graph, the graph of triangulations and that once punctured surface, then generically you would get a pseudo-analysis. We haven't written that down, but it doesn't give you the statement we were after, which is the word metric.
Okay, let's thank our speaker again.